Well, hello everybody from 510-610. This is Dr. Keith Schubert. We're talking today about performance scaling inside parallel programs. This is not a topic the book covers anymore. It used to, but I think it is a good one to understand. To kind of set up the stage for this, what we're considering is, imagine you've got some large cluster. It could have a bunch of GPUs on it. It could be multi-core. Could just be a standard cluster. I'm not worried as much about that, but I've got this large cluster and I want to run a problem on it. Now, often when we have really big problems like this, the type of problems we're trying to run are usually scientific in nature. So there's a few basic ones that we use. We tend to use things like, let's say, for instance, Barnes Hut, which is used for simulation of galactic systems or something. Or maybe I'm doing an FFT, a fast Fourier transform. I could be doing an LU factorization, which is a standard type of way of doing a matrix factorization, and it's similar in its scaling to a lot of other matrix factorization problems. Or I could be doing another one that's quite popular nowadays, things like an ocean or atmospheric simulation, which are used typically when you're considering climate change and things of that sort, or trying to simulate waves in the ocean, things like that. So let's consider the waves in the ocean problem. Just an example to get the scaling. So I usually like to start by doing a little problem setup. I kind of got a small amount of space here, so I'll try to see how I can move my hand around without the camera. So let's imagine I take the ocean and it's inside, the part I want to simulate is inside this box. And so I kind of draw my lines up and I'm going to grid them out. And these are different sectors of the ocean that's in here. And, maybe on these I've got, some type of a coastline that's here or something like that, whatever that's going on. So I've got some type of an ocean pattern. And inside these little grids are going to be a bunch of different points that I'm going to simulate the ocean height at. Now, I could theoretically just use every one of these points on one machine and just calculate all of them as it's going on. But I would like to split this up, and let's say I want to assign each of these grids to one processor or something of that sort. So, I've got to consider how is this problem going to scale as I add either more processors or if I add more grid points if I want to get higher resolution that's going on. So we want to think about if this is being handled by a single machine, right? So we'll say that we have n points that we are evaluating at it and p processors that's going on. So this is going to be one processor. This is a second processor and a third processor, so on and so forth. All right, now given that kind of setup, let's see how much computation has to be done. Now, the computation has to be the number of points that each processor gets. So if there's a total of n points, let's move this up a little bit so I have some room here. So if I have a total of n points and there are p processors that they're divided between, then the number of computations that I have to do is going to be equal to n over p, assuming that I only have to do one computation for each point. Now in reality, I'm going to have to do a whole bunch of computations. There'll probably be some memory accesses, and I might do this over and over again repeatedly in time, which that gives me then that my actual number of computations I'm going to do is going to be this times some, let's say, alpha computation. And this then will give me basically, I can scale this alpha computation with a bunch of different things. I could pick that alpha computation to be just number of computations for one particular time through. I could consider this to be how much time I spend on one time through, so I could get the time that was spent on computation. So it kind of depends on what I pick this scaling coefficient that goes on. Now in reality, each one of these points here, let me pull this back down, I've got a point, and in order to do its calculation, I kind of need to know what all of its neighbors are doing. Now, internally in the system, it's really easy to transfer data between these ones. That's internal to the system. It's only RAM. That's quick and easy. But this transfer that's going across here is, this system needs to share its value here, and this one needs to share with that one so they both know what's going on, because I don't want the height of the ocean to be discontinuous across the boundary. If I just consider inside here, it just follows these own areas, and there's no guarantee that what happens here is compatible with what happens here, so I could get weird discontinuities. But they know what's going on between them. I can get a nice, accurate solution. They'll track each other well, and that's wonderful. Now the question is, how many of these little transfers have to happen? Well, if you think about it, that's all the ones on the borders have to talk to each other. And if they transfer here, you can transfer information up here too by just this one knows about it and can let it know. So essentially, I've got things that are proportional to one side. Now, we could go, okay, great. I could just take this and say, well, it's then half the perimeter as it goes on. Now, your perimeter, when you think about it, is proportional to the diagonal. Now, you might wonder, why do I want to make that assumption? Well, because otherwise, number one, I have to actually figure out what is the approximate ratio. And we usually try to keep this fairly square, which means I have a pretty good idea what's happening here. But if not, and I go rectangular or something, again, trying to factor it's kind of a pain, but taking the diagonal gives me a good idea what's happening inside. So if I use that assumption that it's going to be proportional to this diagonal, which gives me an idea about what this is. Again, it's not exact, but it at least will give me a scaling factor. And it is proportional there. So we say, okay, great. My communication areas, let me get this up so we can get there. So the communication that I have to do, that's going to be, to get a diagonal, that's the square root of the number of components there are. Well, the number of components is n over p. So therefore my communication is going to be proportional to this. Now, again, I could take some scalar, alpha communication, and if I pick this to be proportional to how many messages or how many bytes I could get, number of bytes transferred, or what's going to be more interesting to me is I pick this one to be the scale of how much time it takes to do. So it will consider in the time of flight and the rest of this wonderful stuff, and that'll give me the amount of time on this. Now we're going to make the assumption that essentially I have two things I have to do. That I have to have a certain amount of time that's spent on computation, and I also have a certain amount of time that is spent on communication, and that I probably have some type of a barrier set up. So therefore I can consider these somewhat separate. Now in reality we're going to try to hide these and all kinds of other stuff, but even given that, there's going to be a certain amount where I am just held up by communication and a certain amount where I'm just held up by computation. So given this, as we're going on, I can say, well look, that is going to be the total time of my calculation. Now we know that the time of our computation, if we take alpha comp to be the amount of time spent in just one single one of these thread calcs or one of the little sub points that's in here, times the total number that I have to points that I have to work on, plus I take alpha communication, and again I assume that to be a time-based parameter, times the square root of n over p. Then what I get as a result is a nice simple equation in terms of the number of points and the number of processors. Now, if you look on systems that talk about this, what they'll usually tell you is that Ocean has scaling factors for computation that is n over p, and communication, which is square root of n over p. And it's all very mysterious to most people, but now you've actually seen it's actually very trivial to get this. You could do this same type of a behavior for any problem you wanted to do. You just break up how am I going to do it and figure out how much each processor is going to have to spend the time doing and how much data communications per one goes on. Now let's see if we can solve a problem with this. Now what we want to do is now create something. I'm going to actually do this on my computer, and I don't know how well this is going to work here, so hopefully this is not going to be too horrible. I have my monitor set up, and I'm going to have to see if I can get this to show nicely. So you can tell this is definitely the homegrown movie theater here. Alright. So to kind of help us out, I've got set up, well, let me just, maybe I'll shrink this to fit because it's kind of hard to get them to go nicely in here. Alright, so this is in Scilab, and Scilab is a mathematical calculation routine, just like or library, just kind of like MATLAB is. So it gives you an environment for which you can rapidly do matrix computations. And we're having to do a bunch of linear algebra equations, and therefore we are dealing with matrices. So let's imagine for a sec here that I've got some system that follows these basic rules. And let's say that I know the number of points that I'm going to be doing my calculation on is going to be equal to, let's pick something like, say, 40,000. Alright, so I'm going to be evaluating the ocean at 40,000 points. And this is really a small section of the ocean, but maybe we're doing this for an initial test to see how big of a cluster do we need, how efficient is our code, whatever. The number of processors initially I'm going to do, let's just pick something small at first. Let's just say I'm doing it on a small test cluster. I just got 4 nodes that I'm going to be working on. Now, I need to actually calculate these ratios, so I'm going to have, you know, my ratio 1, and ratio 1 is going to be n over p, just like we have calculated here. Now, in addition, I need to know the square root of this. So I'll just call this SQR1, square root 1, and that's going to be the square root, and it recognizes the term of R1. All right. Now, this is kind of my first setup. Now, in order to be able to estimate, I'm estimating 2 parameters, alpha computation and alpha communication. That's why I want to be able to get from doing test runs, because what I'd do is I'd set this problem up and I'd time it, and I would get some t answer back to this. Right? So let's say I set this up and tested and I ran it, you know, whatever, I'm going to simulate this for a day or whatever worth of stuff. And so I end up that my full simulation, let's say, takes 22 minutes, just to pick a time. Now let's say I take this thing and I say, okay, I'd like to do the same exact problem, but this time I would like to change the number of processors to be equal to, let's say, 16. So I significantly increase my processors, although this is still a very small number, and I would like to calculate new stuff. So let's say ratio 2, and that's going to be n over p again, because I've changed p, and I've got square root 2, which is going to be square root of R2. Now, what I've got set up here is this first one up here, ratio, is proportional to the amount of computation I have to do. Square root 1 is proportional, this is proportional to the amount of communication, and then R2 is with the new setup. I've got more processors, which means I'll have less computation going on, and I'll also have less communication total between any 2 ones, but I've got more of them actually happening. So, you know, this one is scaling a little bit different as it goes. Now, let's say on my new one, you know, if everything was ideal, you know, and I was only dealing with computation, then I'd be down somewhere around 5 minutes or so. Let's say in this case that, you know, I've got my new time, let's call it time 2, and let's say that gives me 6 minutes. So I have, slightly above what it would be if it was just computation. So maybe I'll call this T1 just so I have distinct names between the two of them. Now I need to set up a way to solve this. So in theory what I've got, let me turn this down here for 1 sec. Will get me holding this by hand. Hopefully this isn't too ugly. So for my equations here, if I take these and I say, I take this equation and I say, great, I've got T1 is equal to, and the alpha comp is always the same. But I do have different communication amounts, and I do have number of processors and that to change. So I can say, look, this is going to be the n, which doesn't change, and I can say over, my P1, which is 4 in this case, plus alpha comp times n over P1 square root. That should be com. And I get T2, right? And T2 is going to be the same alpha comp times n over P2 now, plus alpha com times square root of n over P2. Alright, so I've got these are my two equations to solve for my two unknowns. So putting this into a matrix formulation, I get T1, T2, and that's going to be equal to, and I'm going to factor out this is common for the columns, so that's got to come out. And so that'll be here, alpha comp, and alpha com is the other column, so I'll pull that one out here, and that just leaves the first column, which is n over P1 and n over P2, and the second column, likewise, I've got the square roots, so I've got the square root of n over P1 and the square root of n over P2. So I've got this nice little linear algebra set up. I know these numbers, I want to solve for these. So that's the problem I'm setting up. So I'm going to make a vector T that holds these. I'm going to make a matrix A, and then what I ideally would like to do is to then solve for this. Now you could do this by LU factorization like we had mentioned before, as long as the system is reasonably decent in its condition number, you'll get a good answer from that, and it's very fast. If it were a little bit worse, I could do like QR factorization, stuff like that. But this all kind of takes a little bit of work and thought. So right now we just want to get an answer quick, and we're trusting it's fairly decent. So we'll just let the machine solve it ourselves. If I call this A, and I call this T, and this is my unknown, right, which I'll call X, then X, in terms of our matrix notation, I want to do a left division into T. Right, now there is no true division in matrices. However, this is kind of the standard parlance. What it means is multiply by A inverse on the left. So if you take that notation as a basic one, which is pretty standard inside numerics, then this is what I want as an answer, and there's pre-built solvers inside any decent routines like MATLAB or Scilab, and they actually use that same backslash operator. So I've got this set up here. Now, what I'm going to do, let's see if I can get my hands around the keyboard here now. I need to set up that matrix T, or vector T, and vector T is equal to, and now we have to set the vector, so square brackets tells us that I'm going to set a vector up here, or matrix. So I want T1, and I want this to be a column, so then I put T2 below it. It uses the spatial awareness to figure this out. Alright, and then I'll set up A. Now in my case I don't have to write all the n's over p's and that. I've already calculated this out. So I need to put in here R1, that was my first one, and then I had the SQR1. Those are my first row, and then I had R2 and SQR2. Knee-jerk reaction, I keep wanting to type square root. So now I've got A and T. So now I can take this and I can say I want to find out what is A into T. And I will call that X, just given an assignment. Right, so now I've got to save this. Alright, and that's in one of my research folders. So I'm not going to save it there. So I'll just stick it here and we'll call it, a 610 example dot SCE. Okay, and then I'm going to tell it to save and execute. It tells me over here it did execute it, and then I can just ask it for what is X. Now it tells me my X is 0.002, that's my computation amount, and 0.02, that's my communication. And you might be going, okay, lovely, what does that mean? Well, what that means is if I take A and I multiply it by X, I should get back my T vector, which was 22 and 6, and my times were 22 and 6, which means that this alpha comp and this alpha com account for correctly this piece of data. Once I know this, and you're like, okay, wonderful, what does that do for me? Now I can kind of predict if I want something bigger. So let's say that I now say, lovely, I now know what these are. So instead of having to multiply by a known here, I could take the same thing and expand it, and I could say, now I want to know what happens if, let's say, I make n bigger. And let's say I want n to go not just 40,000, but, let's see, that's 40,000, 400,000, 4 million. Let's kick it up to 4 million points that I'm going to do this in. Let's say I have a bigger cluster. So let's say my P is now equal to, and maybe I want, I don't know, maybe 64 nodes that's inside there. So now I need to calculate my ratios. So this will give me R3, and R3 is going to be N over P, and SQR3 equals, and now we have to do the square root of that. Okay, and so now I've got my vector of complexity. All right, how big is the problem that's going on here? That's equal to R3 and SQR3. And then from that, I can now calculate my time. So T new to do this is going to be equal to my complexity. And I'm going to multiply that times my vector x, which tells me what the coefficients are that converts it. So we will save this and tell it to execute, and then I can ask for what is T new. And it says it expects that I should be able to finish this problem with those changes in 130 minutes, so just over 2 hours. So I could use this to kind of gauge how big of a cluster do I want. I could change the number of processors and see how at time I get an idea that's somewhat close, because this actually scales proportionally with my problem size. As it goes, unlike Amdahl's law, this will give you an idea of how the problem's difficulty changes, as it's going to relate to the processor division and the rest of this. So how much time should it spend on computation and how much on communication. So this gives you an idea of how you can do that. And this is your first example little lecture, and I'll record another one in a few minutes here on the next topic. So hopefully this helps, and I will see you all on Friday. Have a good day.